Hello, this is video 61. I'll be talking about angular momentum. This is the last topic here dealing with rotational motion where we're finding the rotational equivalence for the linear quantities that we talked about previously. So angular momentum is the rotational equivalent of the linear momentum that we defined earlier, which was P equals mv. We said whenever an object has some velocity, it has some momentum. So now we just do all the usual substitutions. M becomes I, moment of inertia, and V becomes omega, angular velocity instead of linear velocity. And that gives us I times omega, which is angular momentum. We use the capital letter L. The units for angular momentum are kilograms times meters squared divided by seconds. This comes from the moment of inertia units, which were kilograms times meters squared. And then omega has radians per second. So since radian is unitless, we just put divided by seconds. So what are we going to do with angular momentum? Let me just show you this picture here. What I had here is, this is called a Lazy Susan turntable where you rotate it so you can reach all of the food. So the reason I showed this picture is to show you the relationship with this quantity and the linear quantity. When you're rotating it, you're applying a force that's causing a rotation. So that means that you're exerting a torque here. And a torque is what causes the turntable to have some angular velocity. So the torque is giving you some angular momentum. So this is very similar to what we learned before, where we had the impulse cause a change in momentum. Remember that tennis rackets, you applied a force to that ball, you made that ball move, you gave it to some momentum because you were in contact with that ball for some amount of time. Same thing here. A torque causes a change in momentum, and that angular momentum is given by I times omega. Now we can look at conservation of angular momentum. So this is how we're going to see angular momentum used. Just like with the regular momentum, we did a lot of collision problems using conservation momentum. Well, here, this statement here is just saying when momentum is conserved. Angular momentum is conserved if the net external torque is 0. Just like with our regular momentum, when we had no force, no external force on the system, our linear momentum was conserved. So we're going to set it up using initial angular momentum equals the final angular momentum. I initial omega initial equals I final omega final. It's possible to have more than one object, but I have just written it this way. But if you have more than one object and you want to break it up into I1 for like this, I1 initial omega 1 initial plus I2 initial omega 2 initial, etc., and then equal the same thing for the final. A lot of times, when we're going to use conservation of angular momentum, is we have one object, such as an ice skater, and she's bringing her arms in. And you know from experience, when she brings her arms in, that she ends up spinning faster. So what she's doing is she's changing her moment of inertia. Can you think, is she making that moment of inertia bigger or smaller when she's bringing those arms in? Well, she's making it smaller because the mass is distributed closer. So the final angular momentum is smaller. So that means, the final moment of inertia is smaller. So that means that if the angular momentum must still equal the initial quantity, it means her angular velocity has to be greater. And that shows that when you bring your arms closer, you spin faster. So those are the types of problems that we're going to do using conservation of angular momentum. There's no external torque. When she brings her arms in, those are all internal forces. So we can use conservation of angular momentum.